Yeah, thanks to everyone for joining. My name is Jeppe Hallgren. Today I'm going to talk about next generation web servers, specifically how you can make them secure and how you can quickly build them. There will be sort of a workshop element to this, and it will be available at this link in the bottom right corner. I'm sure someone can post it in the chat, as you also have it there. We will get to the workshop part later, so don't worry too much about it for now. But what this talk will really be about is probably how we as bioinformaticians can share our research. So quickly, something about me. My background is I did my undergrad in computer science in the UK. Mostly did some research on recurrent neural network and other types of new machine learning methods. Then worked a few years in industry and eventually decided to come back to academia. So did a master's degree at Copenhagen University in bioinformatics. Specifically on all the things protein structures plus machine learning. I was extremely fascinated with how much publicly available data that exists on protein structures. And I also built a framework called OpenProtein. It's on GitHub if you're interested, which is basically an extension to PyTorch, specifically for making predictions on proteins. But doing this degree, I kind of learned a lot of things about bioinformatics. And one thing is doing the research itself, but just as important part is how do we actually share this with other scientists so they can benefit from it. And that is basically what I've been working on for probably the last 18 months. It's basically thinking about how can we really benefit from each other's research. But if we take a step back, so in traditional science, typically you would go into your lab and you would do some experiments and get some interesting results. And you would then write about them in a scientific journal and publish it for other people to read. And this, of course, works relatively well. It's a good way to share knowledge. And we can cite each other and benefit from each other's work. If we look at a field like computer science, it's typically slightly different. Of course, you still do your research and you still publish a paper, but you'll probably also open source your code, for example, by uploading it to a public GitHub repository. For example, there's this great project called Papers with Code, where for lots of new machine learning papers, basically the code will be attached. And this typically works pretty well, right? Because the consumer of this research is typically also another computer scientists who are used to dealing with code and quite easily can benefit from the research relatively quickly. Unfortunately, fortunately, it depends how you look at it, we're not so lucky in bioinformatics. Right, so in bioinformatics, most of the potential users of our work is actually traditional biologists or chemists or lab technicians or everything in between that may not have the technical ability to benefit from someone's work in bioinformatics, typically because maybe you've written your code in Python or R or Docker or some technology that most people who haven't dealt with data science directly are able to really benefit from. So while they can read your paper, the work itself is not so actionable because they can't really run it. So what do we do about this? So a relatively old idea is this notion of web servers. So if you were to ask a software engineer about web servers, they would probably have a different idea about what it is than when you ask a bioinformatician. But typically, if you ask a bioinformatician, the opinion is probably going to be something like what's on my screen right now. This is Primer 3, a really great tool for making predictions or analysis of potential primers. And the idea is basically if we can just create our bioinformatics research in the form of a website, people generally, at least in 2021, know how to use websites, and they can literally just paste whatever sequence or molecule or other type of data they're working on and press run. Then they can actually benefit from our research. So it's a really neat idea, and it's used a lot in some cases, but there's also a lot of cases where it's not really used. And I'm especially interested in those cases. So let's go a bit back. What would it actually take for someone who has done some bioinformatics research to turn this into a web server? On the right here, we have the scientist again, who has collected some data from the lab, and then now want to run your code, if DNA, that's so original, Essentially, for that to happen, you need to create this thing in the middle. Let's call it a web server, which can read in the scientist's data, forward it to your algorithm, run the algorithm, and return the result back to the user through the web server. And while it might look simple on this diagram, it's actually fairly complex. Specifically, among many things, some of the things you need to do is you need to host this server somewhere. Right, so it needs to be a physical server running somewhere, serving your code. You need to develop a web front end, so the visual thing the user actually sees when they use your tool. Now, the bare minimum you'll need to learn is probably things like HTML, CSS, JavaScript. However, speaking as a front-end developer, there's tons of other tools you may want to learn as well. Then we come to the backend of this. Of course, in order for you to actually process the user's data, you will need to map whatever user input is provided to you to what your program expects. Now that you're running your code suddenly on the server instead of your local laptop, you'll need to make sure it can actually run in multiple places. And finally, if your code is going to be used by a lot of people, you probably want some kind of queuing system to make sure that the server doesn't break if two people use it at the same time. So this is a lot of work you need to do as a bioinformatician just to publish your code. And I really think that's a shame. But actually, it gets even worse. Because what about data security? Right, this was kind of the thing that 20 years ago people didn't worry too much about it. But today, especially in the industry, bioinformaticians typically is in, data can be extremely sensitive or proprietary. So I may have a secret molecule I want to analyze. It may be because I'm about to publish it or patent it or something else. I can't just be broadcasting it to an unknown third-party web server. It could also be that the data is actually at a hospital, and for legal reasons, that data can't leave the hospital. Right? Then it's not going to work to send it over the network to this web server. And finally, we have rules like GDPR. If there's any type of personal information in this data, again, you need to make sure that the web server is GDPR compliant. Lots of things that you, as the researcher, you shouldn't have to worry about these things. And I think one of the reasons, or one of the consequences of this is basically that people don't create web servers, or most people don't create web servers. And I think that's really a shame. It means that lots of bioinformatics out there that no one just ever use. Luckily, people are quite good at open sourcing their thing, but I think in my opinion, most potential users, they can't go on some public Git repository and actually benefit from your code. They need to have it accessible in some other form that's more approachable. And of course, as scientists, we also miss out on an opportunity here for impact. That's the obviously short-term thing that the more people who can access your research, the more people will cite it. But also as a scientist, we have this greater mission to push forward the knowledge of humanity. And there's a quote by Newton here that we can only really win by standing on the shoulders of giants. So it's very, very important that we actually solve this issue for the greater good of bioinformatics in general, because otherwise we just won't progress very fast. These were some of the problems I was wondering about when I finished my degree 18 months ago. So what I did, I got a few friends together and we started this project called BioLib. So the idea is, creating web servers is not great right now. Can we do something about it? Can we even come up with some sort of editor where I quickly, with a press of a few buttons, actually can turn it into an actionable web server that other people can benefit from? So on the left here, we had sort of the editor view. So on the top, there's the source code. It looks a lot like a Git repository you might have seen elsewhere. You have your files, and you can view the content of those files. Below, you have the web server settings. So these are the inputs you typically need to ask your user about. Right? Each web server is different. It can vary a lot what type of input data you might expect. So you need to be able to configure that. And then on the right here, you actually have the live view of the web server. But I think I might just show you how it works in practice instead. So here I'm logged into the framework, and I can basically create a new application. I'm going to select Python for this particular project. So this is Python 3. And the first thing I see here is the source view, where I can see my files. Just for the sake of this example, I'm going to go with a relatively simple web server. So this particular web server just reads in a name using argparse, and then it prints. We can change this to hello there, and then that particular name. I then want to configure the input, and actually I've cheated a bit. I've already pre-configured an input here, which again is called name. It's a text input, and the description should be what is your name. We could change this if we wanted, and we might have some default value. Again, I could add additional inputs here if I wanted, specifically for files or drop downs, whatever I might need in order to allow my user to give me the right data. Other things you can configure what language you've written your tool in. Citation might be extremely useful if you're creating something you would like other people to cite you for. So let's just put in some data here, like this, 2001. Great. And now you can save it. And then basically that's all that's required to create a web server. So right now I have this link up here. I in principle could share with anyone, so my colleagues or academic peers, and they would be able to go onto this web server and right away run it. So you might enter the name. And then with no installation required on their side, they can basically run my algorithm and get the result. So how does this work? I'll just go back to my presentation here. Great. So I also wanted to make this sort of a bit of an interactive workshop. So I've provided this link you can go to, link.biolib.com/ngws, not to be confused with next generation sequencing, but this is next generation web servers. If you'd just like to get started, you feel free to mute me or turn the volume down on me and try that out. In the meanwhile, I'll go through some of the technical things. How does this actually work? And then afterwards, I'll go and actually do the workshop as well. So if you get stuck, you can just wait for me to catch up. This particular challenge is about building a secure web server to convert DNA to RNA. Relatively simple task, but the point is more such to get a feeling with how this actually works. It's split into 3 subtasks. One where you just replace one base pair with U, and one where you implement a reverse complement feature, and finally one where you change it to accept a FASTA file. So relatively typical workflow for a web server, except of course in most real-world cases the algorithm is going to be significantly more complex than just converting DNA to RNA. Great. So again, if one of you want to get started on that, feel free to do that. In the meantime, I'll talk a bit about how does this framework actually work. So I think the first thing I realized, this all really starts with security, because if you're willing to sacrifice security, that's a lot of hoops you can jump through. Right. So the problem we have again here is that the user has some data on their system, and your algorithm list is on the web server, and somehow these 2 things need to talk together. But you want to do it in a way where you sort of protect the privacy of the end user. That's absolutely critical for them actually being able to use your web server. So I think generally speaking, there's 2 options here. Option 1 is where instead of sending the data to the web server in clear text, you perform some kind of transformation on the input data. So I wrote encrypt on this slide. There could also be other types of transformations that essentially would still allow the web server to do its work, but it wouldn't reveal anything about the data. Then the other solution is basically just flipping this arrow in the middle. What if instead of sending the data to the web server, what if the web server could send the algorithm to the data, right? What if the algorithm could run client-side on your own machine? That would suddenly solve a lot of things, because now the data never leaves your computer. So security is basically as good as it can get. So let's start up with the first option. So we need to apply some kind of transformation to this data, so that the web server doesn't learn anything about the data, but can still do its work. So the first obvious one, which you may think about, is anonymization. So the idea is, can we somehow remove sensitive information from the data, such that we can still do our work, but don't violate GDPR or anything else? I think generally speaking, this is very hard, especially in our field, right? Take something like, assume you had a spreadsheet with, one column was the person's name and the other columns was their full genome, right? Just removing the name is not going to give them anonymity, right? Because, genomes are fairly uniquely defined individual people. So I think, generally speaking, anonymization doesn't work so well, especially not in bioinformatics. The next thing is an idea I was very fascinated with in the beginning. It's called homomorphic encryption. The idea is basically, can we encrypt the data in such a way that we can still perform math on it? So basically, think of it as taking your input data, really seeing it at just, like some point in space. Can we map it to some other mathematical field where mathematical operations still apply? So we still do addition, subtraction, etc. But in this other mathematical field, the data is unreadable. That's roughly the idea of homomorphic encryption. It's an area we explored for a long time. Unfortunately, today, it's still a quite novel technology, and it's still extremely slow. So we spent a lot of time optimizing it, but I think it's still at least 1,000 times slower than traditional compute. And then finally, the last option here is something called secure enclaves, which we got extremely excited about. So it's a relatively new thing. So most modern CPUs, so if you've bought a computer within the last 5 years, it most likely has a secure enclave inside it. You can think of it as sort of a hardware chip next to the main CPU that can run verifiably trusted code. I'll get back to what this means. But what's quite nice about it is it only runs on encrypted memory. So if you were to look at the chip at the time of computation, you wouldn't actually be able to see anything because it only works on encrypted memory. Now, what this allows us is to go back to our original idea here. We want to send some encrypted data to the web server. If we can encrypt this data client side and send it only encrypted directly to the secure enclave and make sure decryption only happens inside the secure enclave. Actually, we could do arbitrary computation inside the enclave then, re-encrypt the result, and send it back to the user in such a way that the web server itself never learns anything about it. So to be more specific, again, this may make it too technical, in which case it's not so important. But basically, we will generate an encryption key pair inside the enclave. Again, remember, the web server itself can't read inside the enclave, so it can't read this key pair. We'll send a public key to the user. The public key will encrypt their data using the public key, send the encrypted data back to the secure enclave for computation, where the data will be temporarily decrypted, computed on, and then re-encrypted the result, and then the result is sent back to the user. Sorry if this is a lot of steps. I guess I can show it in practice if you're interested. So here, let's see, I think I have an example here. I'll just refresh. So this is pretty much the same application as you saw before. It takes in a name and then computes something on it. But this runs using a secure enclave. So basically, what you saw before was running client-side, and I'll get to that later. But this particular case is running on a remote server, but inside a secure enclave. So what's happening right now is basically that the enclave is being spun up. It is pulling in the source code of this particular web server, because we need all of Python and a few other dependencies that will take a bit of time. Then we start up the encrypted enclave. The image will afterwards then be sent to the enclave, and then we'll do something called attestation. And attestation is basically the process of verifying what codes runs inside the enclave. So the main idea, if I as a user trust that code, I'm happy to send my data to it because I know it doesn't do anything bad with my data. So that's essentially what's happening right now, is that my computer is attestating the enclave and making sure it runs only the right data. Sorry, this went a bit quickly. Whenever that's finished, the data is being encrypted on my computer, sent encrypted directly to the enclave, compute happens, result, hi there, Jeppe, is being re-encrypted and then sent back to my computer. So this is sort of end-to-end encryption in a way you could say, which makes sure the web server doesn't learn anything about your data. Of course, the dream with BioLib is that you as a bioinformatics researcher shouldn't have to worry about all this complex encryption. You should just be able to build your web server, and then this should just work. So that's at least the mission I'm working towards. Anyway, going back, the other solution, which is instead of sending our data to an encrypted enclave, what if we just send the algorithm directly to the user and actually compute on the user's computer? Again, I don't think this is necessarily worse or better than secure enclaves. I think they both have their merits. Of course, if you're doing something very compute intensive, you can't assume that the user will be able to do that compute on their own laptop. And in other cases, you might have data that for legal reasons cannot leave the network, in which case the client-side option is the better. It's really up to you as a developer to judge, what mode is the right for you. So how could this work, right? So we still want to have a web server. That was the whole assumption of this, that we need to have people need to be able to access our research in an easy way. But now we want to run this complex code inside the web browser. How can we possibly do this? We have this thing called JavaScript, which in principle is Turing complete. And for the computer scientists in the room, that means essentially that you could, anything you could compute with any other language, you could also compute in JavaScript. In theory, in practice, of course, things like Python will not run directly in JavaScript. So what can we do about that? So one very neat technology that came out, I guess it's almost 3.5 years at this point, is called WebAssembly. So the main idea is, let's have a shared assembly language for the web. Right, I don't know if you know, but most CPUs have their own assembly language. But of course, when we're on the internet, we all have different computers, so we need something better than that. And so a group of organizations came together and designed this. And actually, for a couple of years now, it's been supported by all major browsers. It executes almost at native speed, and it has really wide support for many different languages, which of course, we as bioinformaticians, we tend to work with a lot of pipelines, right? And these pipelines are typically written in a wide range of languages. So the last one here is very important. To give you an idea about the speed, it's a very early version of BioLib. I think this screenshot is probably 16 months old, where we took SAM tools. SAM tools is one of the most used bioinformatics tools in general, I think. It's being used typically as part of genotype calling pipelines. In this particular case, I tried running SAM tools stats, which is a subcommand of SAM tools, on a 350 megabyte BAM file, so a relatively large input file. When I ran this directly on my laptop, it took around 6.14 seconds. When I ran it through WebAssembly in the browser, it took 10 seconds. So it's slightly slower, but it's not really by a lot, right? Most people, for most compute jobs, would be fine with waiting that a few extra seconds. So this is actually very promising, right? Because if we could do this, in principle, we could almost run an entire operating system of bioinformatics apps directly on the user's computer. And to them, it will appear just like any other website. That said, if you try to get started with this, you quickly learn that actually compiling things is hard. That's sort of the whole motivation for this, that we can't assume that our users themselves can compile things. Specifically for WebAssembly, a lot of libraries are still not supported. Multi-threading sort of works, but not really. There's a lot of browsers to support. They might interpret the WebAssembly standard slightly differently, even though they shouldn't. And finally, most tool chains are still in beta. That said, not all hopes is lost. What we basically realized that we had to do was that we had to do a lot of work pre-compiling libraries. Right. So first of all, if many of the common bioinformatics tools were already compiled to WebAssembly, when you were building your pipeline, you could basically just stitch them together without you yourself having to deal with the low-level compilation. Then we also realized that some languages are not actually compiled; they're interpreted. And again, without going too much into technical details, basically, there also had to be compiled a number of interpreters to actually get this to work. Finally, you have a lot of files, input, outputs, graphs, visualization things. Lots of things need to be dealt with. So I also spend a lot of time getting that to work nicely. Cool. Yes, and below here you can see a couple of different languages that is supported. R is still very much beta, but Python should work pretty well. Cool. So I hope this was not too much shorter. Now we're basically ready to move on to the workshop. Some of you might already have gotten started on that. But if not, I will basically do it on my screen here. So I'll start off by going to this link.biolib.com. Oops. / next generation web service. Great. And this basically will have all the tasks. So the first task here is that we want to create a very simple web server that takes in a DNA string and converts it to RNA. So In practice, that basically means converting all T's to U's. So let's try to do that. So like before, I'll create a new Python application. So let's configure inputs first. So in this particular case, we want to take an input sequence, a DNA sequence. Text input is fine. We say insert DNA sequence. We do want to require our user to specify it, and as default value, we can type something in here. Great. Now to actually use this, we use argparse. Again, if you've written a Python program in the past, you've probably used this already. If you're new to it, it's fairly simple. You just add a parser and you say what particular arguments you're interested in. To see if this works, let's try to maybe just print DNA and then args.sequence. Actually, I'll just put this into a variable for later use, just to see if we can actually read the input correctly. Great. And then I just save it. And then to test it, we can run it here, and we can see it nicely renders our input. I'll just type in a test sequence to see if this works. AGAT. And again, this runs inside the client side, and indeed it does print out my input sequence. Okay, so now let's go to the next step, which is essentially translating it to RNA. Now, because this is a text string, it should be fairly easy to work with. So I should be able to do something just like this: RNA equals DNA dot replace, and then we'll replace all T's with U. Just see if I get that right. Like this. So again, relatively simple stuff, but of course, this is going to get increasingly complex. So let's see if this works. So now I input my DNA sequence, ACG. Let's get some C's in there as well. And we can see this actually seems to work quite nicely. It will convert all the T's to U's, but all the other bases stay the same. Of course, when I'm testing it here inside the editor, it's in this pop-up window, but I still have this link like before, which I could share with anyone else, which actually is the web server itself. Yeah, I can also just update the README here. Oh, sorry, the README, with some more interesting text in case someone wants to find my web server useful and wants to run it. So now this is updated, and again, this is Markdown, so you could really have whatever you want here. Okay, let's try to go slightly more interesting. So let's say, for the sake of argument, what you might want to do here is, before you just replace T's with U's, you might want to calculate the reverse complement DNA string before you convert to RNA. But we want to make this an optional feature, because maybe not all users want to do this. So we'll add a toggle where people can essentially toggle this feature if they want to. So to do this, I'm going to create a new type of input down here. So let's call it RC for I can spell it correctly. We don't require the user to specify this, and the default value could just be no. So if I save this now, you will see that the form has been updated, and users will now be queried for this particular type of input. So they can say, on or off whether to calculate this. Of course, right now we haven't actually written any code to deal with this input, so it will just be ignored. But let's try to do that. Like before, when we read the input sequence, we now need to read one additional input argument, which is called RC. And now I should be able to do something like if args.rc equals to yes. Like, this is basically when we want to compute the reverse complement. Computing reverse complement essentially means mapping all bases to their complement base, while at the same time reversing the sequence. So because we need to do a bit of magic now, I'm actually going to start off by converting the DNA string into, so I'll just move this down here. I'm going to start off by converting DNA string into a list of bases. So let's say we have a base array, which is just a list of all the letters in the DNA string. Okay, so the first thing I want to do is probably reverse the sequence. So let's do, say, DNA reversed should basically be the reversed of my base array. The next thing is to do this mapping. and I think this should be here as well in its tutorial. You want to map all the bases to the complement. So to do this, I think it's probably easiest just to iterate through the list of bases. So let's do for, and actually I'm also going to have the position as sequence here. So I'll do for position, comma, base in, I don't know if base is a research keyword, I'll just do a letter here. And then I'm going to enumerate over my reverse sequence. And then we'll just have an if condition. If the letter is A, we'll map that to T. And here I'm just going to directly replace the position in my base array with that particular base. Again, you could probably write this in a million different ways, but this is just one. So great. And I now need to do this for all the other 4 bases. So I'll just quickly do that. T to A, and we'll map G to C, and finally C to G. Great. Okay. So now we have this base array, but we probably need to go back to a text string like before. So to do that, I can basically join an array in Python by saying empty string.join, and then joining that on the base array. So this will basically join my list of base pairs into just a single string, and then I do my replacement again of T to U. This should work, though it's always dangerous to write code live on the screen. So let's see if it works. I'll just try now first without actually toggling this reverse complement. So now I should not do that, not do the reverse complement, and it looks like it indeed haven't done that. I still just replaced T's with U's. So now let's try toggling this thing and see if it works. So I think this is the correct reverse complement. Right. So the complement of A is C, and the complement of T is U. So I think this works. Might be mistaken, but you basically get the idea. I was able to relatively simply now build up this input form and actually do something with the input. Okay, so let's take this even further. So let's say it's kind of nice to have the user input a sequence now, but most often users will have their inputs in the form of a file, right? And especially when we talk about sequence data, it typically could be in the form of a FASTA file. So let's try to do that. So right now, the sequence was given as a text input, but let's try changing it to a file input. Actually, there's this type called text file input where you can both enter text and files. So we'll do that. I'll not have a default value for now. Now, the change here basically is that instead of getting a string in now, we'll get a file name, right? Because the user will now provide us a file. So before I could just do args.sequence to get out my sequence. Arg.sequence will now be a file name. So what I instead need to do is actually read that file. So let's try to do that here. So I'll just do open and then say read, and then .read. If this works, it should now basically read the input sequence from that file instead of just being given as a text string. So let's see if this works. So we can indeed see that things changed here. Instead of just having a text box, I can now select a file. I can also input text. That's why it was called a text file input. So let's see if this works. The main difference now is that my program will be given the sequence as a file instead of as just an input argument. And actually, down here, you can open the application log and see what happens if you're interested. And more specifically, it will show you what input the program is being run with. In this case, you can see that the sequence argument was this, which is just a file name. But the good thing is my program still seems to work. Okay, and this, of course, is fine if my input was just a sequence of base pairs. But in this particular case, we want to support the format called FASTA, right? And what is FASTA? FASTA looks a lot like that, except typically has the first line be a comment, and typically there's a length restriction on the width of each line as well. Luckily, there's other smart people out there that have created nice libraries for us to use. So if I can recall this correctly, I can, from a library called BioPython, whoops, this is almost correct. From BioPython, I can import a package called sec.io, I think. And if I'm not entirely incorrect, I think I should be able to do sec.io.read. I might have to Google this if it doesn't work. Which should give me back the sequence from a file. And this takes in a FASTA file, so it should work. But let's see. So this time I actually have to supply a real FASTA file, otherwise it's going to complain. So I'll just now select a file on my desktop, which is just called dna.fasta. But let's see if this works. It did not. Oh, sorry. And you also get an error message if you do something wrong. In this particular case, it complains that it's missing one argument for read. So it's probably because here I have to tell BioPython that this is a FASTA file. Let's see if this works. Again, I could also just type in my FASTA file here if I wanted to. Great. So this looks like things actually happened. So it read my FASTA file, and it also printed out the reverse complement of my RNA string. Cool. I think that's basically the end of the workshop. Of course, you could do many other things like plotting or returning files back to your user. I guess that's the only thing I didn't actually show you. So whenever you run this thing, it's just like running the thing locally. It will, not only print some results, but you can actually also save the files, which will give you back the files in case you have saved, let's say, some kind of transform FASTA file or whatever the user might be interested in. Great. I hope that makes sense. Just to finish off before we move to the Q&A. What's next for me? One thing I learned is that bioinformatics is an extremely wide area. There's many different types of coding projects that can be done. So almost every day there's a new challenge at hand. It could be new programming languages or new types of transforming data. If this sounds interesting to you, please join. I've set up this community Slack where you can basically ping me directly if you have any feedback or if there's particular type of input you may be missing to build your web server. One other thing I've learned is that hackathons are actually great for bioinformaticians to get together and collaborate. It's basically a way for us to exchange ideas and build on top of each other. So I'll also just finish with small advertising. So together with a group of great organizers, including the Copenhagen BioVikings, we're going to create a hackathon at the end of April. It will be virtual because the world will probably still be shut down, specifically focused on protein predictions. So not just folding, but lots of other interesting things like what characteristics can we predict from a protein structure and how can we predict protein-to-protein interactions. Cool. That's all I had. But this is my email, and always feel free to write to me if you have any questions. Great. Let's see here. Marek, do you want to go over to the Q&A?
Yes, thanks a lot, Jeppe. This was a great presentation and nice workshop. Also, real life coding. Nice, everything worked out. Really cool. We already have, maybe I'm just gonna share my screen just so it's there. We already have some questions in the chat. So what I will do is I will first try to give the chance to the people to actually ask the question. So if you want to do that in person, please use the raise hand function, and then we'll invite you. And if you don't want to do that, I will just read it out for you. But I'll give you a second or two. Seems like Johannes doesn't want to do that, so I'll just read out his question. He says, how do you support homomorphic encryption? For example, we need to calculate meta-analysis using sensitive data from a number of clients, like public hospitals. We thought to use homomorphic encryption in order to send hospitals data, encrypted data, and after that calculate meta-analysis in encrypted data and send back the results encrypted?
Cool. Yeah, that's a very interesting question. So I think generally speaking, you need to differentiate between whether if there's multiple partners or parties or just one party, which want to do with the compute. Right. So in the case of just a single hospital, this is fairly easy. You basically just create your algorithm. You have the hospital encrypted the data using the secret key on their side, send the encrypted data to the server, process it there. Again, based on my knowledge, you should be able to do almost anything in homomorphic encryption. There's a few exceptions, like you can't really do conditionals, because if you could derive what the data was. But other than that, you could do almost any type of computation. I think what this particular question gets at is, what if you have multiple hospitals? How would it work then? And that's a much harder problem. And actually, there's a whole area called federated learning, which is specifically on that. How can we basically distribute the learning of our machine learning out to different nodes in the network, do the training there, and then collect that to a collector model, but very importantly, without the data ever leaving the nodes. I could talk for a long time about that, but I think what the person wants here is probably something called federated learning instead of homomorphic encryption.
From Octave. So Octave, if you want to ask your question, you can just raise your hand. Yes, so I'm going to ask for you, what kind of Python libraries does BioLib support other than BioPython?
That's a good question. So I think that's actually a documentation page. If you're interested, that should list them. But most common data science things, so things like NumPy, SciPy, Matplotlib, etc. If you need something more, so this is specifically for the client-side execution. So where you actually need to go and compile those libraries into WebAssembly. For the enclave type, you can do anything. So actually, in my demo, I was running a Docker image that was based on Python and TensorFlow, but you could replace that with any other Docker image. So really, there should be no limitations on the number of things you can run.
That's very cool. I think I actually have a question of my own. And
sure.
I was just wondering, when you have these secure enclaves, it took quite a bit of time to run that whole thing, right? So I was thinking, does that time change with the input data size or the complexity?
Yeah, that's a very good question. Actually, the main thing we're working on right now is how do we make that faster? I think for most web servers, you should be able to get feedback, within a few seconds. Whereas now I think it's 1 or 2 minutes. It's something I want to work on making a lot better. Actually, most of the time now went on downloading the Docker image into the enclave. Right, in my particular case, I ran this Python plus TensorFlow Docker image, which is actually very large. I think almost 0.5 gigabyte, and that's why it took so long. Or in many cases, you can use much more lightweight Docker images like Alpine, which can a tenth of the size. So you could do many other things to make that a lot faster. And I think it should certainly be possible to go less than 30 seconds in the startup time. The compute itself should be near native, so it should run as fast as it would do locally. And the really nice thing about being in the cloud is that really there's no limit on the amount of compute you could get. You could get 64 cores if you needed that. Which is a big advantage over client-side execution, because then you really never really know what your clients have.
Nice. That's very cool. We have a raised hand, so I'm going to hand over the mic to Cass.
We'll see if this actually works. But yeah, I was wondering if you were to run, like you mentioned, it's also a possibility to send the code basically to users' own computers to run it locally, which of course depends on them actually having proper computing power for that. But let's ignore that for a second. To what extent do you think that's feasible with algorithms that you can't actively share? Because I can imagine you as a company as well are like not everything you're gonna be working is like open source and just all on GitHub. Sometimes you might want to implement things that you have access to, but you don't necessarily want to like send to everyone. Can you do that and still combine that with the idea of sending it to users themselves to run it locally?
Yeah, that's a very great question. Actually, we have a few users which are companies that still wants to make their research available to other people, but can't share their code because that's kind of their proprietary information. And I think the enclave use case is a really great case for that, right? Because with the secure enclave, basically both parties can exchange information without the data owner revealing the data to the algorithm owner, and without the algorithm owner revealing the algorithm to the data owner. So it basically allows two parties to collaborate without revealing too much information to each other. We are considering if we could move the enclave to be physically out next to the user, right? So not only is it always end-to-end encrypted, but also the data never have to leave the user's local network. But that's currently work in progress.
Yeah, I can imagine that would make like GDPR things and stuff much easier. But cool
Indeed.
to hear.
Yep.
Very nice. Thanks for your answer.
Cool.
Hi, can you hear me?
Yes.
Okay, cool. Thank you for the really interesting talk, and I'm already looking forward to the next hackathon.
Awesome.
I was wondering whether you could tell a bit more about how you turned this really interesting and really like constructive idea into a business. And I saw that you have a lot of open source stuff like Muscle on the in BioLib, and I mean, these are like open source stuff, and I guess you can't earn any money with that. So I guess you have to host like stuff from companies to earn money with this actually. So I was just wondering how this works.
Yep, that's a very good question. I think for now, I'm not particularly concerned about that part. Again, I'm really doing this because I believe we as bioinformaticians should have an easier time sharing our research. That said, of course, we are also lucky to be in an industry where we have lots of large pharma companies that will want to use this and probably will want to use this in more advanced ways than a typical researcher. So a typical researcher might be fine to sit in a web browser, but maybe a large company wants to run this on their entire database of molecules, which may be in the hundreds of millions. Right? So I think there's lots of use cases where you as an organization can generate revenue, but for now, we're mostly focused on the academic side. I think that's the most interesting one.
Okay, cool.
Jeppe, would you be able to share maybe some facts about your journey as well? Was it easy to have set up your own business, do a startup, and all of these issues? How is it going for you? Also, sure, this last year. Crazy stuff.
It's a very good question. Yeah, I think for everyone, it's been a crazy year. I mean, I've always thought it to be fun to build new things. So for me, it wasn't a particular big mental jump to go out and turn it into a larger project. I think this is too important for the world that it has to happen. So I'm very happy to work on it, no matter what. But there has been lots of ups and downs. I think right now I was actually hoping to be in Boston. Boston is this great hub for life sciences. But as you know, the world shut down and we've been home for almost a year now. But I think everyone in the team is really looking forward to get back and meeting people. Also, just because again, we've done a lot of virtual hackathons and they've been great. But a lot of it is also just meeting new people and creating new connections. Yeah, so I think we're all really looking forward to things opening back up again.
That's very true. Cool.
Awesome.
Let's see if there are any other questions. I don't see anything. Then maybe that's the end of it. Thank you so much for the session. It was pretty interesting also to see work in the real time.
Thanks for organizing.
I'm just going to close everything off with a few more details. We always are looking for new speakers. So if you are someone who would like to give a talk, please go to our speaker sign-up form. You can maybe take a screenshot of this page and use the QR codes or just use the links. Or if you know someone that you would like to hear speaking, you can go to this recommend a speaker form and tell us who you would like to hear, and we will contact them for you. And again, if you want to talk about the events on social media, please don't forget to tag us, #NordicCombio, and that way we can keep in touch. Thank you all so much for coming to the session, and thanks again to Jeppe. And good luck with everything.
Thanks, Marek.
Okay. Bye.
Bye.